Hi, it's me, Jessica, again. Welcome to today's Science Short. Today we will be learning about how we measure the wind. I'm outside in the North Findlay Wind Campus yard next to OneEnergy's weather station. In the last Science Short episode, we learned from Ben, who introduced us to the different instrumentation or tools we use to collect data here at the North Findlay Wind Campus. Today, we'll focus on two types of instruments that allow us to measure the most important data we have to collect: wind speed data. There are a few ways to measure how fast the wind is blowing, or wind speed. The two we are going to learn about today are called cup anemometers and ultrasonic anemometers. So how exactly do cups and something called ultrasonic work to tell us how fast the wind is blowing? Well, let's first break down what the words mean. Both instruments are anemometers, which means they measure the wind. A cup anemometer uses small cups to catch the wind to determine how fast it's blowing, and an ultrasonic anemometer uses sound waves to determine how fast the wind is blowing. Cup anemometers have been around for a long time, even as far back as the 15th century. They are quite simple and are regarded as the gold standard in wind measurement. Ultrasonic anemometers were developed in the 20th century and are a bit more complicated of a technology. They use ultrasonic sound waves, yes, sound waves, to record wind data. Even though these two instruments are very different technology, they both do the same thing: measure the wind speed. Let's go find out how they both come to the same conclusion in very different ways. Here I've got a cup anemometer. It's called a cup anemometer because it uses these pieces shaped like cups to catch the wind. The cups spin around the shaft when air flows through them in any horizontal direction. The faster the cups spin, the faster the wind is. So how exactly do we tell how fast the wind is blowing by these cups spinning around? Well, we have to count how many times the cups spin in a circle over a period of time, or the rotation frequency. To do this, anemometers typically use a reed switch. A reed switch is an electrical switch that's activated by a magnet. The switch is located on the shaft, and the magnet is located on the spinning part of the cup. Each time the magnet passes by the switch, it closes the switch and allows the electricity to flow through for just a moment. The electrical pulse then travels down a wire and into our data logger, where it records the rotation frequency. Computer code stored within the data logger then translates the rotation frequency into wind speed in meters per second or miles an hour. Each model of cup anemometer is slightly different, so the rotation frequency translation depends on the specifics of the exact instrument. Now let's look at an ultrasonic anemometer, commonly referred to as a sonic anemometer. Sonic anemometers work differently than cup anemometers. On this instrument, there are no moving parts. Instead, sonic anemometers detect differences in the time it takes sound waves to travel through air. Sound waves, or sonic pulses, go from one part of the anemometer, the transmitter, to the opposite end, the receiver. When the anemometer is outside, the wind is able to blow through the path of the sound. The sonic transit time, or how long it takes for that sound to travel through the air, is impacted by wind speed. If we know how long it should take the sound to travel through the instrument without any wind, we can compare that transit time to the transit time traveling through the wind. The difference between these two allows us to calculate the wind speed. This is where our handy data logger comes back into play. To translate the sonic transit time into wind speed, the computer code stored within the data logger uses some equations that relate the sonic transit time, velocity of sound in still air, the distance between the transmitter and the receiver, temperature, pressure, and relative humidity. This model behind me is a 3D ultrasonic anemometer. We use this model here at the North Findlay Wind Campus. It has 3 sets of transmitters and receivers, allowing the anemometer to calculate the wind speed coming from different directions. OneEnergy uses different instruments to measure wind speed. We use cup anemometers, sonic anemometers, and LiDAR units, which we'll cover in the next episode. All 3 of these methods can accurately tell us how fast the wind is blowing in certain areas. We use all 3 because each one has its strengths in different situations. Cup anemometers are very simple and work well to validate other types of wind measurement, but they don't always work well in extreme conditions, like when it's really cold outside and ice builds up on the cups. Sonic anemometers don't have any moving parts, so they're more robust and can hold up to extreme conditions, but like cup anemometers, they have to be installed on a tall tower. LiDAR units, on the other hand, are very mobile and can be placed anywhere we want to know more about the wind. Having all three at our disposal allows One Energy to accurately determine an area's wind resource. That's it for today's Science Short. Tune in next time to learn more about how we use LiDAR to measure wind speed. And just like always, remember to challenge everything.